All right, so now we're going to take a look at this idea of the average atomic mass for the elements. And when we talk about the atomic mass, what we are referring to, just by the name itself, is the mass of the atom. And what it represents is the mass of that atom in a specific unit called the atomic mass unit, right? Or AMU is what we abbreviate that as. And the AMU is defined, one AMU is defined as 1/12 the mass of a particular isotope of carbon, which is carbon 12. Okay, so that's what atomic mass represents in terms of the particular unit. Now, if you recall from the earlier sections, we know what an atomic mass unit is in terms of grams, right? So an AMU is an incredibly small mass. Remember now, these are masses of atoms, and atoms are incredibly small. So they have very, very small mass. So it's about 1.66 0.5378 times 10 to the negative 24 grams. So it's a lot more convenient to work with AMUs than with the actual gram number for the atomic mass units. So when we see an entry in the periodic table, for instance, so let's take a look at, we looked at sodium before, let's take a look at sodium here. You'll see that in addition to the atomic number, right? So remember 11 here for sodium is a Z, that's the atomic number. The other number that you see in the periodic table entry is this number here. That's usually a decimal, and that is the atomic mass. It's not the mass number, it's the atomic mass of that particular element. And that is in AMUs. Okay, so what this is saying is that if I consider all of the naturally occurring isotopes of that particular element, and most of the elements in the periodic table exist as a mixture of isotopes. Okay, this is that atomic mass that we see on the periodic table. That's a weighted average of the naturally occurring isotopes of that element. So the weighted average mass of the naturally occurring isotopes of that element. So it takes into account all of the different isotopes. It takes into account the masses of those isotopes. Remember now, isotopes differ in terms of the number of neutrons, and neutrons have mass. So the isotopes are going to have different masses. And it also takes into account how prevalent or how abundant those isotopes are in nature. Okay, so for example, if we take a look at another element, carbon, we see that that carbon is a mixture of these two, occurs naturally as a mixture of these two isotopes. We have carbon 12, which has a mass of 12.000 AMU, and this occurs 98.93% of the time. So what this means is in a random sample of carbon, if you had a sample of carbon, 98.93% of the carbon atoms in there would be carbon 12. And the remaining 1.03% would be carbon 13. So when we determine now the average atomic mass, the way that we do that is we take into account the percent abundance, right? That's a natural abundance of that. We multiply it by the mass of that isotope. And then we're going to sum that to the percent abundance of the other isotope times its mass. And then we keep doing that until we've accounted for all of the isotopes of that particular element. Okay, and I'm going to say dot, 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 dot. So this percent abundance here that we incorporate into this calculation, this is represented as a decimal. Okay, so for example, 98.93% is the same as 0.9893. So for carbon, we multiply that percent abundance times its mass. So these two are multiplied together. And then we add it to the product of the percent abundance and the mass of the other isotope. If there were other isotopes present, we keep adding those on at the end. And we'll see that for carbon, the average mass of carbon then is 12.01 atomic mass units. And if I look at my periodic table, guess what? For carbon, we'll see that that 12.01 is shown on here, right? So some periodic tables go to more decimal places. Some go to 2 decimal places. If we did, it would be 12.01 AMU. So notice the mass here, the average mass of carbon is neither the mass of carbon 12, nor is it the mass of carbon 13. It's somewhere in between, and it's actually closer to the mass of carbon 12 than it is of carbon 13 because the carbon 12 is more abundant. So it makes sense then that the weighted average is closer to carbon 12 than it is to carbon 13. So note that it is not a regular average or a mean, it's a weighted average. Okay, and this is really key. Because it takes into account the percent abundance. So it would make sense then that the overall weighted average mass for carbon is a lot closer to 12 than it is to 13 because carbon 12 with its mass is way more abundant than the carbon 13. So we can make some, we can draw some conclusions, make some inferences based on what we see here. How do we know that there are these different isotopes, and how do we know that one isotope is more abundant than the other? Well, we use a device called a mass spectrometer in order to identify what's present and how much of that thing is present. So this is a schematic of a typical mass spectrometer. And if we look at, oops, lost my page. If we look at a typical layout of it, so we're going to inject our sample through this end over here, and the sample needs to be turned into a gas to begin with. As it goes through, it gets zapped with an electron beam, and what it does is it converts your sample into something with a positive charge. Right? So we have these positively charged species that are produced over here, and then they are accelerated through this region. And as they are accelerated through that region, they are then going to be deflected through two charged plates, and the amount of the deflection, or the degree of the deflection here, is determined by their charge to mass ratio. Okay, so the degree of deflection of the ions depends on their charge to mass ratio. Okay, so you have your sample coming in. Sample needs to be a gas. It's zapped with this electron beam. It converts it into a positively charged species. That species is accelerated through these two charge plates, positive, negative charge plates. And as they are deflected, the degree of deflection is determined by their charge to mass ratio. So ions then that have a small charge to mass ratio will be deflected more than those that are bigger, essentially those that have a larger mass. So when these particles are deflected, they're detected over here, and as the ions hit this detector, they generate a current. And when they generate a current, the size of that current tells us the relative amount or the percentage of that particular isotope that you have. So this would be a typical mass spectrum. For example, this is the spectrum for neon. Okay, so we'll see here then that the mass, this particular sample of neon, we have way more of the neon 20 because its peak is much greater. So the current generated then is greater over here than it is for the other two peaks, which represent the other two isotopes for neon. So this is the device that allows us to come up with or to determine these values that are provided in this particular table. Okay, so the number that you see on the periodic table, that's typically a decimal, that is the average atomic mass for that particular element, and that is derived by taking into account the percent abundance of the different isotopes for that particular element. So if we take a look at an example of how we can calculate the average mass. So we're told here that oxygen, so oxygen is O, most abundant element in the crust in the human body. The atomic masses of its three stable isotopes. So we have oxygen 16 with occurring 99.75% of the times, oxygen 17 occurring a small percent of the time, and then oxygen 18 a small percent of the time as well. And then these are the masses associated with each of these isotopes. If we need to calculate the average atomic mass of oxygen using the abundances provided, we can go ahead and calculate those, right, using the same formula like we did previously. So the average atomic mass of oxygen. Okay, so we're going to take the percent abundance of oxygen 16. So that would be 99.75%. Expressed as a decimal would be 0.99757. I'm going to take that, I'm going to multiply it by the mass of oxygen 16, okay, which is given as 15.9949. And I'm going to add that to the percent abundance of the other isotope for oxygen 17. It is 0.038%, so expressed as a decimal. Move it 2 decimal places to the left, so that would be 0.00038 times its mass, which is 16.9991 AMU, and then we do that for the third one. So we have percent abundance for oxygen 18, so 0.205%, expressed as a decimal will be 0.00205, times it by its mass, which is 17.9992. And then we just evaluate this, right? So we multiply out, and then we add, and we end up with 15.9994 atomic mass units as your average atomic mass. Now, does that make sense? Well, if we look at the percent abundances of all of the isotopes, we'll see that oxygen 16, this one, is way more abundant than all the other two isotopes. So if we take that into account, then the weighted average should be a lot closer to 16 than it is to 17 or than it is to 18. And what do we find? Yes, that's the case. The weighted average here is very close to 16 compared to the other masses. So it makes sense, right, based on the number that we end up with.